Let me turn the proceedings over to Professor Cerf, Dr. Professor, or Dr. Professor.
Hairless doctor.
Yeah.
Hairless doctor. That would be me.
Thank you. Perfect time.
How are you?
Good to see you.
Well, good afternoon, everyone. My name is Vince Cerf. I'm your chief internet evangelist, in case you didn't know that. So may all of your packets land in the right bit bucket. It's a real pleasure for me to introduce Jim Gettys, who has an interesting and varied background. He used to be an astronomer, but he's been corrupted by computers like many of us have. And as a consequence, he joined Digital Equipment Corporation, and he worked on something called Project Athena, not the one that you know of currently, but another one many years ago in a galaxy far, far away. But in the course of that work, he was one of the creators of the X Windows system, something which if you don't know about, you should learn about. And the reason is that a lot of what we do at Google, in a sense, is X Windows on steroids. If you could think of HTML5 as being a way of producing a visible result from some remote processing system, which of course is our cloud paradigm. So his background and experience is very much in keeping with some of the philosophy that we have here. He was the editor of the HTTP 1.1 spec, which had a very important effect on our business because it lets you have one server with many, many different websites, whereas before that didn't work out very well. He worked on Linux for handheld PDAs, something which should resonate with our Android experiences. After that, he became, among other things, vice president of One Laptop Per Child, which I think some of you will know we were involved in to some degree in helping to bring to fruition. So he ended up at Bell Labs, and he says he's supposed to be working on immersive teleconferencing. But one of the things that this triggers is a desire to understand why the network doesn't support accurate and adequate teleconferencing. And it is in consequence of trying to use his home network to do this sort of immersive two-way interactive collaboration that he encountered the now famous Bufferbloat problem. And so I think this, even if there is debate on the conclusions that Jim has reached on this subject, it's important to know something about the symptoms which he's uncovered, because it may have a severe impact on our own ability to deliver timely services. And we all understand that Google is all about low latency. And so anything that gets in the way of latency will get under Larry Page's skin. That's not where any of us want to be. So if this is an issue that we need to do something about, Jim is the guy to help us understand it. So Jim, I turn it over to you, and I thank you very much for taking the time to join us today.
This really started as a personal history. I really need to acknowledge many, many people who've helped along the way. And in fact, some of you have helped and helped provide pieces to this puzzle. My apologies if I've overlooked your contributions. We'll take it from there. So I've been assembling a puzzle, and the way I've characterized it is something that many of you may have heard. The internet is slow today, Daddy. I know I did with my family again and again. And I would go try to debug my network, and the problem would typically go away. Though a number of times I was able to get it to go on long enough that I was making support calls to my ISP and all that sort of stuff. So about a year ago, I was trying to prove that the antique blue box, a few of you know what that is in this audience, needed to be thrown away. So I was playing with it and doing simple-minded tests, performance tests, but also monitoring my latency. And I saw this horrible behavior of 1 to 2 seconds latency with very rapidly varying jitter. And since I tend to be a systematic type, I then tried the same thing without the blue box. And I got the same result. And this was bizarre. At the time I was busy, so I had to put it on hold for a couple of months. And I got back to it sort of late last June or early July. try to figure out what was going on. In the intervening time, for the third time in the last 3 years, lightning had struck near my house, and all of my existing home network kit had been blown up again. And that actually plays into this story because I tended to have the latest and greatest hardware, whether it be Ethernet switches or cable modems or the like. Also made it more entertaining to try to debug. So I want to take us back a little bit in history for a moment to the 1980s and 90s. In that era, those of you who lived through it with me remember that we had really severe congestion problems all over the internet and unacceptable latencies. There was tons of research done. There's a whole set of algorithms that go under the rubric of AQM, active queue management, that were developed at the time. The most widely, most famous and widely deployed is one called RED, which we'll play into this later. But in any case, around the late 1990s, things seemed to ease down, in part because a lot more fiber got into the ground. So people actually caught up with the demand, at least temporarily. And RED was deployed, people were turning it on. And so, in fact, the congestion problems we experienced really went down to a dull roar. And so a lot of us, myself included, thought the problem was solved. This is probably old hat to most of you in this audience, but sometimes I get surprised what people do and don't know. So one of the properties of TCP is it will fill any buffer just before a choke point in a network path, given enough time. And there's an unstated design assumption in TCP, which is that if there's congestion, there will be timely packet loss, which allows it to react. It's an end-to-end servo system. Okay? If you don't do that in a timely fashion, it destroys the congestion avoidance and the control loops in TCP. And we judge other transport protocols in general, TCP is just one of quite a few, as that they are at least as good as TCP. We judge they may be reasonable to deploy into the internet. So now I ask the questions. What happens if this timeliness assumption is violated by a lot? And, you know, if you're working hard and trying to avoid packet loss, lots of engineers think that dropping packets is evil. We shouldn't ever do that now, should we? But in fact, in a congested network, it is essential for timely packet loss right now, because we don't have ECN deployed, to occur for the network to function correctly. Okay, so you'll see this map a lot in this talk. I have to talk about things all over the internet. You'll see the same map again and again with different things circled to try to keep you from getting completely lost. So here I am at home on my poor little laptop talking to a machine to MIT. It's almost exactly this network configuration, though there were a couple more hops in the middle than this particular diagram. That's almost exactly what my initial tests were doing. So I'd seen this problem in April, and I'd been trying to chase it, but lightning had done me in, and I was having trouble reproducing it. So I'd try to find out what could be doing funny things to my network, and I was suspecting Comcast's, I think they call it Powerboost. And so it turns out that Rich Woundy lives in the adjacent town to me, and I had already sent him mail saying, hey, let's get together for lunch. And in the morning, I was going to have lunch with him. I finally figured out how to reproduce my problems again. But that lunch was really covered a pile of topics, and he handed me a bunch of puzzle pieces. One of which was, hey, there's this big buffer problem. Dave Clark had warned him of this several years before. He'd been trying to chase it, and he'd never been able to prove it. Pushing back on vendors to keep their buffering minimal, but it's hard to do without good proof. And we explored topics of how I might rule in or out the Powerboost feature and so on. He also told me that, to my surprise, that red wasn't always turned on. I filed that away for future reference. That surprised me. I thought it should be. He also told me there are issues around ECN, such that it's never been properly deployed. He also gave me a pointer to the ICSI Netalyzer project. Any of you, whenever you go to a new network, should, as the first thing you do, run Netalyzer to find out what's broken about your network that you've just sat down at. It's a nice little Java thing that tests as much as the Netalyzer group can figure out how to test in about a 5-minute period. And it will tell you all sorts of wonderful things. So I highly recommend it. That Vint is how I was able to know that even without looking at my interface, that IPv6 wasn't on Google Wi-Fi. So the real smoking gun I got was the next day after lunch, after the day of lunch. This is a wonderful tool called SmokePing. And so I happened to be copying or rsynching the old X Consortium archives from my house to MIT over this 10 millisecond long path. And if you look at this, SmokePing is both reporting latencies averaging well above 1 second, okay, along with bad packet loss, just while copying a file, or actually a whole pile of files. It's about 20 gigabytes of stuff. And the only times when the latency is low is because trying to surf the web or read mail was so painful, I occasionally suspended it just so I could do something else. This is the daddy, the internet is slow today problem. You can do it to yourself. I was doing it to myself. I just realized then how to reproduce it forever. So in any case, I decided, having in a previous life, that I probably should have packet capture and look what was going on, because this looked very bizarre to me. On a 10 millisecond path, I should see maybe a millisecond or two of additional latency, but not a second of latency. So I just took Wireshark, and there were these bursts of really strange behavior I could see, periodic bursts. I could see that just in SmokePing, in Wireshark. And so I resurrected, after several weeks of looking around, my old skills at TCP trace and XPlot to be able to plot it up graphically so you can actually see what's going on. And so I did that. What I got, this is, by the way, what's sort of an optimal single TCP transfer is supposed to look like on a properly functioning network. Instead, what I got was this. Okay? There are a number of things to note here. Why is there something like a quarter or half megabyte of data in flight on over a 10 millisecond path? Why is it doing this horrific burst things, which is exactly lined up to all the weird things I was seeing in the packet capture? All this sort of stuff. This is over a period of minutes, by the way. Why is it oscillating at like 10-second periods? I mean, this looked like no TCP I expected at all. Should never occur that way. Okay, so the next week I went down to New Jersey and played around with my in-laws' FiOS service. Okay, and so where I am now is playing around with their home router, basically provided by the FiOS guys, and both wireless and wired, and doing the same sort of, capturing the same sort of data. It's not as clean because I wasn't able to lock the family out, so there was some cross traffic. But I got this out of that. Guess what? It's very much the same sort of thing. It happens to be several hundred millisecond latency over a 20 millisecond path. Again, this is bizarre. And over wireless, things were even much worse. So if you look at it in detail, it has the same sort of signature. But again, 400 millisecond kind of latencies out of this and the like. So I'm seeing this stuff, and my cable's not working right now. FiOS isn't working right. What's going on here, guys? So at this point, having had to stare at TCP to some extent in the 1990s, I knew enough of the right people to call for help. And I did, to a bunch of people, including Greg here, and later Dick Seitz, but a bunch of other people as well who looked at the traces in more detail. Van looked at the data as well. It turns out that since I was using Linux on both ends, there were even timestamp data in the data sets I already had. So, and after about 2 weeks of of discussion, we CC'd Vint on this. We even had to accept that congestion avoidance had been defeated by all of this. Note that classifying traffic can't really help you. There's only a single queue in these broadband devices. There's no way, the telephony services that a carrier provides, an ISP provides, is being separately provisioned from your data service. You have no way to cause your VoIP traffic to preferentially go over your data service in any of the broadband stuff right now. And it fundamentally can't help you. All that would do at most is to move when and where you get pain. A little bit more later. Okay, here's the key data set for broadband. At ICSI, and I'm very, I'd like to thank them very much for the ability to use their data. This was stuff published last June at NANOG, and again later this fall. And this particular set of diagrams is split out by different technologies. You can see cable, DSL, and fiber. And it turns out if you look at these carefully, you can see that there's bad latency in all of the technologies. And in this case, green here is half-second latency. Everything above this is more than half a second. Now, the normal telephony standards for good audio is actually only 150 milliseconds. So if we took this, drew a line where 150 milliseconds would be, it would actually be back here. Now, the other thing is this is a lower bound. It turns out there was a bug in Nettleizer, and it would sometimes miss identifying the buffer sizes. So the latencies are often much worse. This, by the way, these black lines are 4-second latencies. Okay? So the broadband is edge, and all the technologies is broken. The only question is to what degree. Not a pleasant situation. What triggers this? All you have to do is to saturate your path. Got to fill the buffers. That induces the latency. The latency while they're full. So this can be all sorts of things. YouTube uploads, or I once caught Google Chrome, with my permission, uploading its dead corpse to Google for crash analysis. My network went to hell, and I looked at what it was doing in the background, and by God, Google Chrome was uploading its corpse. Email with large attachments, BitTorrent, about that later. File copies, backups, potentially things like CIFS, lots of other things, video teleconferencing, so on and so forth. And I'll talk more about web browsing in a little bit, which is another interesting topic in and of itself in this area. Okay, so latency isn't the only thing that happens here. This is also inducing abnormal packet loss, but not hugely dramatically so, but it seems to, at least on my circuit, do so in bursts, which is not so great. But this causes timeouts on lots of low-level protocols. So if you've wondered why you've seen occasional DNS lookup failures or DHCP failures on busy networks, this is pretty good reason to believe it's this sort of stuff. What you want to do is to think, what protocols are you involved in which have those presumptions of timely behavior that's now being violated by Bufferbloat. Of course, gamers hate latency. They know this more than almost anybody. So ICSI has proven the broadband edge is just plain broken. But unfortunately, I've gotten really paranoid, and I think it's almost everywhere. And I'll try to prove this to you now. And I hope you go away as paranoid as I have been since about last October, or even before that. I feared in August, in that mail exchange, what I was going to find when I poked. And unfortunately, my worst fears were confirmed. So along the way, I caught this behavior on my home router, again by smoke ping. Here, I'm observing 8-second latencies. This just happened to be a time I managed to catch it graphically using smoke ping. I can induce it trivially, as I describe in my blog. So, so I wanted to understand. Okay, broadband's broken. Now, what else is broken? So I think the home routers are broken. So I started doing experiments just around my home routers and the like. So eventually, having tried 3 or 4 commercial home routers, all of which were lousy about this, I decided I really wanted to play with things. And I've been talking to a number of people, including Ted Cho and the like, along the way. I'd already understood that other buffering, like Linux's transmit queue, might be involved. And so I installed OpenWRT so I could actually twist the knobs on my home router. And I remember the day I twisted the knob and absolutely nothing happened. And 2 days later, I finally realized that no, I was copying from my laptop upstream, which means that the bottleneck is the 802.11 link, which means the buffers are in my laptop. And as soon as I twisted the knob on my laptop, the latency started to come down. So anytime your broadband's bandwidth exceeds your wireless transfer rates at home, the bottleneck shifts. Okay? And so you think you fixed it in one place? Well, there's lots of other places it can be doing. So I already have this problem in spades. I happen to have a house with a big chimney. So it's really easy for me to get lower bandwidth at times than my broadband, particularly since in the process of doing experiments, I upped my service to higher broadband service. Okay, well, what's going on here, of course, is that since most of these home routers now are based on general purpose operating systems, that's where this is coming from. And modern OSs turn out to have a laundry list of places where they like to hide buffers without much thinking. Let's do a simple calculation, like 256 packets, which turns out to be a number we see pretty frequently, is of order 3 million bits. So that's even at 10 megabits a second, is a third of a second. Well, what happens when you're at a busy conference and your fair share is 1 megabit per second or less? You can easily go from a third of a second to where nothing works. Okay? So along with the interesting packet losses I also think are probably occurring, though I'd love to see more real data on that. So you may say, as I sort of started questioning myself, why don't I see this on Ethernet? This is an interesting story by itself. So you do actually see it trivially on Mac OS X and Linux on 100 megabit Ethernet. I just plugged my gigabit NIC into a 100 megabit switch, copying just to another machine, saturated the link. And it turns out that our Ethernet drivers typically have 256 packets of ring in there, 250 56 packet entries roughly, plus or minus some, in their interfaces. Windows is particularly interesting because it doesn't happen to suffer from this. I wandered around Microsoft's website. After an hour or so, I discovered that they almost certainly ran into this problem, didn't quite understand it, but put in a very pragmatic thing to do, which is if you're, by default, Windows, all versions, rate limits how fast it transmits to keep from saturating a 100 megabit switch. That explains that. And as soon as, for example, I put the NIC to 10 megabits per second on Windows, I saw of order 250 packets worth of buffering in the driver from the delay. You can do the simple computation. So where does this hurt us? Well, it hurts us in lots of different places. Potentially in your machine rooms, though often not. In our handsets, potentially, and all over our laptops and the like. So it was a grave surprise to me to understand that this kind of queue management is necessary and buffer management is needed in our host operating systems, and it is not there currently. Okay, this is a little bit more complicated, but it's really back to the 1990s congestion phenomena. If you've got a lot of people sharing the same network and there's a lot of buffers all over, they can start to interact. And that's indeed what we see in 802.11 environments and 3G kinds of environments. And so you can see phenomena where the latency goes up as more and more people use the network, and peaking at some point. People time out before the packets go away. So the packets may get delivered, but the people have timed out. So you weren't observing packet loss in the way you thought it was. They're lost because the person's moved on, not because the network didn't necessarily transport them. This is exactly what Dave Reed reported on end-to-end interest about 18 months ago and got flamed out about. I now know that this is true in 3G networks, both in the RNCs and also in backhaul networks. There are problems in multiple places there. Some of our carriers have real problems that they've not fully understood, I believe. Okay, so you'll remember that one of the puzzle pieces handed me is, well, RED's not being used everywhere, and I wanted to understand why that was, or other AQM. So in August or so, I called up Van and asked him. Had a wonderful story, and he tried, Kathy Nichols, about 10 years ago, wandered into his office and proved to him in a period of an hour or two that the RED algorithm is fundamentally flawed. The net result is, as 100 papers in the intervening decade have proven, it requires careful tuning to be used effectively. Since if you tune it wrong, it can hurt you, some network operators have been understandably leery of turning it on when they should. And therefore, some networks are running with queue management to keep the buffers under control in the routers, and some are not. You can get some of the ideas of what's wrong with classic RED by looking at a early version of this first attempt to publish it that did happen to escape onto the internet. It's called RED in a Different Light. The first time they tried to publish it, the program committee didn't like the fact that he used a diagram of a flush toilet to explain the end-to-end servo mechanism in TCP. The second time, it was a blinded review. They got back reviewers' comments which said this can't possibly be reasonable. The authors of this paper should go read the fundamental work on the subject, e.g. Floyd and Jacobson, 1993. Shall we say that Van tried, but it didn't happen. And so now I'm in the unenviable position of trying to encourage them to get this paper finished and out the door, as it has a much more cogent explanation and potentially a better algorithm than classic RED. So where are we seeing this? Well, we're seeing this in any place you've got a lot of wireless networks, and you see it in hotels, you see it in some ISPs. There's a paper characterizing residential broadband networks, which specifically tried to look for queue management in the head ends of the different technologies, and it looks like from that paper about 1/3 of those head ends are running without any queue management as well. Then we have it in 3G, as I've already mentioned. I have no idea what the state of LTE is, but I've also, 3 years ago, was seeing 22-second round trip times over a satellite link to the Ministry of Education in Peru. I mean, lots of places that it ought to be that it isn't. It hasn't been running. In any case, let's do a little bit of trivial math. This is to try to convince you that given the huge dynamic range of modern wireless networks, you need to be very careful. Even when you're sharing that busy network, and you might be only getting a few megabits per second, even a packet or two of buffering is significant. But what happens if you go to 25 packets or more? And then unfortunately, there's various things that the 802 committee thought were good ideas that often are not, like trying to retransmit excessively and stuff like that. So that's a different discussion, but and one I'm not very expert at. In any case, what you get out of all of this is a really ugly behavior, and it's really complicated when you actually see it and look at packet traces. You see this at conferences using 802.11, schools and hotels. All of us have seen the cesspool called hotel networks, and that sort of thing. This is sort of we had the OLPC mesh network and even non-mesh network melt, and we didn't understand. We actually had to set up a full test bed to try to figure out what was going on under load. And we did not understand what this was going on. I now believe it was one of the three and probably the second most important phenomena we were suffering with. Maybe the most important, hard for me to know. at the time. So this is the laundry list, which, of course, the real laundry list is much longer than this. You think about places where packets can hide or buffers can hide, you're almost certainly correct. Wireless chips themselves may have multiple packets of buffering in them. The network device drivers may squirrel away one or more packets. Then there are the ring buffers and that sort of thing. There's if you're running a VM system on top of another, then you've got two stacks potentially of buffers, one on top of each other. So you have problems obviously in your 3G things, your backhaul networks, just again and again. Even what you think of as Ethernet switches have buffering in them. They have to function correctly. Dave Reed pointed out to me, if I remember the number correctly, he said, well, to do a gigabit on a loaded network and not drop packets on a switch, you need 8 milliseconds of buffering, which I hadn't thought about, but it makes sense. So in any case, this gets to be really ugly. There are other places you need to worry about. I was using smoke ping inside of Bell Labs, monitoring our network, and it turns out that we have very sophisticated classification for VoIP and a number of other things, all configured on our routers, and no queue management. So nothing is signaling and controlling the queues by telling the endpoints to slow down. For various reasons, this is going to get worse. I'll go into that, I think, a bit more in a moment. Let's see, there are tunnel devices where you can have this. I've seen this in our IPsec infrastructure. The bottleneck there seems to be where it touches ground in the firewall complex, as far as I can tell from the round trip times. I expect to find it in other places. Question marks are places I haven't actually looked, but expect to find it. Things like encryption buffers, firewall relays of various sorts, you name it. Let's see. So buffers are only detectable when they're next to a saturated bottleneck. At all other times, the buffer's empty and don't hurt you. So you can have buffers throughout your network, and you only get bit if and when that buffer becomes adjacent to a bottleneck. All the other times, they're dark. They don't seem to hurt you. They cost you money and power, but they aren't actually hurting latency. You have lots of these sorts of things. So I think I've gone through most of this, so we'll move on. Let's see, I hit the button wrong. So in any case, where do we have it? Well, as you can see, our poor network map is getting awfully busy with circles, isn't it? You see why I've gotten really pretty paranoid. Okay. So, I don't know, it was 2 or 3, 4 years ago, I forget exactly when, I was noting that the browser guys were changing how many parallel TCP connections they would use. Originally in HTTP, we put a limit in the spec saying, please don't use more than 2 TCP connections simultaneously. The reason why we put that in the spec was, at the time, there were insufficiently buffered dial-up modems in common spread use in the 1990s. And so if you ran a pile of TCP connections at once, you would get horrific packet loss when too many packets arrived at these dial-up modem banks on a loaded evening. So we said, guys, be friendly, do something nice. So when the browser started sprouting 6 or even more connections in parallel recently, I thought about it and was nervous. This is 2 or 3 years ago, but I had no reason to worry about it much. Well, unfortunately, it's a real problem, and it's a problem that's now being compounded at the server end by the changes that various people are making or want to make with the initial congestion window to raise that from 4, I guess the current proposal is 8 or 10. I don't know the exact state of things. And the Google complex, last I knew, was set at 8 due to a mistake I found out the ITF. There was a blog post where somebody who had seen this noted it. The Microsoft website was at infinity. That turns out to have been a broken load balancer, and they've fixed that. So please don't. We're all in this boat together. Please don't don't flame at them at this point. I've been assured that it's been fixed or is being fixed. The problem is, if you go to an image-heavy web page, what happens? The browser opens up a pile of TCP connections and simultaneously makes a request on each, and back comes some number of packets, at least of order 4. And of course, if the congestion window is larger, it may be more like 10 for each of those connections. But of course, with sharded websites, things like that, it may in fact easily be many more than that. Some browsers in some circumstances are doing more than 6 connections at once. It's easy to get 100 or more packets effectively coming back at your poor little, lonely little broadband connection to arrive essentially simultaneously, and they go splat. Now, there's enough buffering there that these buffers that are in our broadband edge will absorb these huge impulses, but it takes a very long time for the bits to trickle out from there. And so even on a 50 megabit broadband service that I now have, I'm observing at times 150 milliseconds of bursty latency when I hit an image-heavy web page. Now, if you ever have delusions you'd like to have high-quality telephony or voice or video teleconferencing, as I would like to have, and I think many other people here would like to have, you'd sort of like it if the other people around you, or even yourself, in routine web browsing didn't cause dropouts in your audio and video, and that you didn't have so much latency in your connection to get around it that it's like talking to the moon, which it often is. We tried to deal with this a long time ago in HTTP 1.1 with a thing called pipelining. It's never been widely deployed in browsers. Almost all servers support it to one degree or another. Opera has had support for it a while. The Mozilla folks seem to be having some pretty successful experiments with finally running it recently, only a decade or more later than it should have been. There's a lot of brokenness that has crept in the meanwhile, so there's yet more band-aids that you have to do to work around the broken websites. In any case, I want to warn people, both working on the web server side and the browser side, the two together are multiplying, guys. We need to step back and think about this multiplication. It's not good to have gone from 2 and 4 to go to 6 or more and 10. Big difference, guys, and we're in the middle of doing this. Is this good? I don't think so. Okay, so then there's some other interesting subtleties about all of this. As I was thinking about all of this, I realized, actually, as Dave Clark, I guess, in conversation said, oh, yeah, BitTorrent would do this too. So I believe, and nobody so far has come to me and tried to claim I'm not right, that at least part of BitTorrent's problems were incorrectly diagnosed in all of this. The buffers were already very large in some of these devices when BitTorrent deployed, and it turns out that Windows XP does not enable window scaling. So it never gets more than 64 kilobytes in flight at once. So it actually takes multiple TCP connections just to saturate a typical broadband device. So I think they misdiagnosed this. And the fundamental regulatory thing from my point of view is that operational problems in the internet should not be able to be kept secret. I think they were getting more and more complaints from customers. They're costing them in the ear with more and more service calls from the kids who were downloading whatever, and their parents were calling up because the network's broken. So that's sort of point one. I think this helped trigger, I've looked at the timing, I think this is true, helped trigger the whole discussions we're now having, sometimes vehement, around network neutrality. The second thing is it turns out that all of our broadband technologies actually don't use the data channels for telephony services. DSL, it's an analog split. The cable guys have put it on a separate channel. Same thing is true, I'm told, about fiber. So this means that conventional SIP, VoIP, or Skype is at a fundamental disadvantage right now to what a ISP can provide. I don't believe this was intentional. I know the network, the conspiracy theorists will have a field day. I really don't believe them. Okay, and I've just been arguing with such a person recently, and I think convinced him. But the fundamental issue out of all of this is if we want to deploy anything with reasonable latencies, if we don't roll up our sleeves and get this fixed, we aren't going to be able to deploy these services and have them actually work. We've got more and more XP is going away, so there's higher and higher fraction of applications are able to trivially saturate these links. And we have more and more applications that are saturating the links. This is getting worse. Okay, so what can you do about it? So some of you, by the time you go to bed tonight, it's somewhat of a pain. You, as when I say you, I'm talking about people in the audience here, the typical hacker here, can start to deal with this. They're not ideal mitigations, but you can help. You can do this a lot, quite easily, with a lot of the middle range or high-end home routers. You'll find buried away under the QoS section sometimes it's called bandwidth shaping, knobs that you can twist, and you want to set them below what your ISP actually provisions for you. If you do that, you can keep the buffers in the broadband gear from filling, okay? At least under many or most circumstances. Now, this unfortunately defeats things like Powerboost, or Turbo Boost, whatever they call it. I never get that right. It also can't fix everything in that broadband connection. But you can go do that immediately, and I'll show you some results of that in a second. You can obviously educate people that, well, you probably need some queue management in your piece of the network. You better turn it on. That's always entertaining because people who deal with operational networks are justifiably very reluctant to go messing around with their router settings, particularly with anything that might ever conceivably hurt them. We need better queue management algorithms. Part of the problem here is that red is not a great algorithm, and Van says it has no prayer of working in 802.11. There are several other alternatives that we're exploring, but we need to get moving on this. So let's see. That sort of thing. So this is where I started, okay? This is the first smoke thing I showed you. So having twisted my knobs comes with some cost of my bandwidth, significant cost of my bandwidth. What I end up with, notice this is still 1.2 seconds. So now I end up with this. Is that a bit nicer, guys? Okay? So there I am with, variants of little, 10 or 15 milliseconds. That's more like it, guys. The 20 milliseconds just happens to be from where this is being observed from. So it really has made nearly 2 orders of magnitude difference in my latency and jitter. That's sort of nice, and many of you could go do this today. First thing you do is run Nettalyzer when you get home, and it will tell you things like buffering. And there's also the measurement lab tools, which are specifically trying to test the specific thing. Okay. We have, yes, Dave. Yeah, that's what I did myself to make my home network work well. Okay? It's not the end of the story because I still have the wireless hop. That was just to make the broadband problem go away, okay? I still got the home router and host problem, okay? Which we have to fix that too. We have to fix our operating systems. That's why the home routers are broken, and so on as well. But if you carefully make sure that you always have more bandwidth on your wireless link than you do on your broadband link, the bottleneck will always be in the broadband link. So if you can't control something, if you can at least shove the bottleneck into a place where you can control it, you can win temporarily. There's very little new here, Dave. This is assembling a jigsaw puzzle. That we've defeated TCP, congestion avoidance, that's a real surprise. There are a few little puzzle pieces I don't think we knew. It's assembling the pieces here. That's the whole bit here. So this whole thing is getting worse. There's this downward compatibility constraint that hardware vendors have. We've gone through multiple generations of Ethernet. And so the values that were selected for to make things go fast over long-haul big pipes to supercomputer centers. That's where the knobs were tested, because that's where the research funding goes, has been to go fast, has caused us to set our knobs for a condition that in fact we typically don't have. And each generation, it's been getting worse. It's not even been scaled by the amount of bandwidth of a particular media at all. So we have this in Ethernet, we have this in 802.11, DOCSIS, so on and so forth. So that's a piece of it. The next is more and more apps are saturating, including web browsers in little bursts, are saturating the edges. XP is going away, so that's good in a lot of ways, but this is why you may have heard reports of Vista or Windows 7 performing more poorly. I know I've seen some of these reports, more poorly on a home network than Windows XP did. Okay. And of course, the other thing is that memory is now just, for most places, dirt cheap. And so people don't even think about it. Okay? So you can't get memory chips small enough if you did. So there's always too much memory. So why don't you just throw it in there, seems to be the attitude. Another major problem is that our typical tests are not testing for latency under load. And so it's not visible to people. So just go to speedtest.net and copy a file from your house to your favorite Google server sometime and see what speedtest.net starts telling you then. You won't like it. But the tests aren't doing that. Needless to say, we've had certain conversations with certain people about trying to cause some of the tests to make this obvious. This is not hard to test for. Then there's this other interesting phenomena we know is going on. If you have a hardware vendor who's making hardware, and their hardware and or firmware is slightly buggy, if they can paper over a performance problem they have to make some arbitrary bandwidth spec by doubling or quadrupling the buffer size, memory's free. We already have it on it. Won't cost us anything. We'll just turn it up to get that bandwidth point. I know this is occurring from talking with people who are in the position of putting people onto an approved vendors list for a major ISP. So that phenomena, this is the one that got Dave Clark really upset. This is the thing where he realized we had to start pushing back on this immediately. So we really have to, and I'd love people to think about this, what's the right marketing metric? They've stolen the speed word from us. Speed used to be really latency, but it's really, they now say that the capacity is bandwidth is speed. It's not, of course. What's the right marketing metric? Do we really need two numbers, or can we invent one that can both somehow capture bandwidth in relationship to the latency as well? Bob Briscoe had some interesting ideas there. I need to push on a bit more to see if we could get to a simple, nice marketing number. So we really have to change the marketing dialogue so that when people go into buy kit in a store, that's one of the features on the boxes. Okay? That sort of thing. But what's the right figure of merit? We really need to have something simple to change the marketing dialogue.
How about bandwidth divided by latency?
Well, it gets complicated. We can have a larger discussion. Yeah, I mean, is latency over which path begins at it? Because are you only measuring the one hop, or right? So you see that's the sort of thing. So I was at the IETF. I gave essentially this talk in abbreviated form at the transport area talk. This is some of the stuff that I put together for that talk of what the IETF should do. People here have a lot of these puzzle pieces that they can help worry about. You can immediately start mitigating problems various places. Please do. Obviously worry about your handsets, both wireless and cellular. If you got any middle boxes of various sorts, you might think about them. Market pressure on vendors. You're in a good place for that too. Browsers. Well, we already had the long discussion about browsers and the like. Be that as it may, but 1.1 is already hugely widely deployed. I don't have anything against Speedy at all. Just 1.1 is out there. In the long term too, but they're short-term things. It might be helpful in the short term. The enemy of the good is the perfect. Okay? It turns out that ultimately the latency starts being more dominated by total number of bits, and running lots of TCP connections starts wasting you bits. Yeah, I understand. I mean, look, I wanted something like, I tried to get people to worry about something like Speedy in the 1990s. I'm not, fine, just get it done is the point. I'm not arguing against it at all. Just, we need it out. We need things like that out there.
It's not even a good thing, but the opposite of the bad.
Be that as it may. In any case, there's lots of research to do here. Can we deploy ECN is an interesting question, given there's brokenness out there. That would be wonderful to not necessarily throw packets away, particularly when you're talking to various wireless guys. The concept of dropping a packet on the floor, they've sweat blood to get across some highly lossy link, doesn't go down very well. Just politically, I can tell you if we can deploy ECN safely, it's going to be a much easier sell in certain parts of the industry. Right. So what all is going on here? I'm trying to wrap this up and get into general questions. Vint asked that I start just getting it out there because conventional publication was going to take too long. So I gave a talk in Murray Hill and at the IETF. I'm here this week, as you know. So it brings you here. Vint asked me to do his next upcoming IEEE Internet Computing editorial, whatever that's called. I forget what it's called. Backspace or something? I don't know. There's a ACMQ case study being put together for this. Some of those papers will end up in CACM. We've set up a website which has bug tracking and mailing lists and all that sort of stuff. One of the possible AQM algorithms is a thing called stochastic fair blue. That had been sitting out of tree in Linux for several years. It's now actually up tree and in the latest Linux release. We need to start testing that. Van also pointed us at some very interesting buffer management work done by folks in Ireland, Tanji Lee, and I don't remember the other guys' names. Tanji Lee is someplace in the United States now. An algorithm called eBDP has been re-implemented and needs testing. I'm actually running it on my Linux machine right now. It does seem to be working better than what we had a little bit later. John Linville, who's the Linux wireless maintainer, is maintaining a deep load testing tree so we can integrate patches for people to not have to necessarily patch the kernel one patch at a time for things. Dave Todd, who's in the room here, has been working mightily recently to get us to the point where OpenWRT can take that kernel and start running more deep loaded. We need lots of help from people on testing this stuff and making it better. At the moment, we've decided that for various reasons, since we've got both operating system problems and device driver problems both, to try to keep our lives simpler. So the initial home router target is a WNDR 3700. It costs about $130. You can go buy one today and help. The cable industry has already started to deal with mitigating buffer bloat. At the IETF, I found out that they've at least now are able to control or will be able in the future to be able to control how much buffering is in the cable modems from the CMTS end. So the problem will get somewhat better. It won't be solved rather than getting worse because they were already testing 150 to 300 megabit modems that would have had buffering. They would have had buffering that when plugged into, say, a 10 megabit per second or provisioned to 10 megabit per second would have been bloated by factors of 15 or 30 at a minimum. So this is at least one step in the right direction is already happening for the cable guys. I applaud them for that. There's just tons of work to do all over our systems. Please come help. Please help. In all the different places. So it's we all are together in this problem. So what's the picture? So, what's been killing latency in the internet? It's the dread bufferfish. For those of you who don't know about pufferfish, they are highly poisonous. They're what the Japanese call fugu, which people sometimes like to slightly poison their lips with, and sometimes more than their lips. So that's been poisoning things. It's bloated, it's spiky, that sort of thing. So that's what's been going on, and it's time for general questions. Yes, Dave. How can YouTube help me? Well, we're recording this talk today, so we need to get it up on YouTube. What can you change? That's an interesting question. When I gave this talk at Apple this morning, there was a person in the audience there who said I should draw to your attention that YouTube seems to be sort of piling as many packets as possible into the network all at once, and that the Flash player that Hulu uses is actually friendlier. Whether that's true or not, I don't know. But it may not be true, as I said. I don't know. Yeah, well, and of course, all these things, when you've got big buffers hidden in various places, means that all your control loops of trying to figure out how they're supposed to behave are going to be really hard to make work well. And they're going to be very all over the map because the amount of buffering is all over the map. Okay? Yes, Dick? Yep, and that poisons all these little protocols, the DHCP, the RA, you name it, all the little background things that don't take much bandwidth. They actually care about those delays. Yes, sir. Okay, so the story I heard from Dave Aran is when I met with him for lunch. He's an old friend. Last fall was that a quarter 10 years ago, there was a certain Taiwanese vendor of home boxes from which a lot of the home kit was descended for a long time and spread, where if it ever saw an ECN bit, it would just out and out crash. And that's not the only instance of that. We've seen some other instances. There used to be an ECN Hall of Shame, which unfortunately has gone missing on the web. The database rotted or something. It used to be somebody who's keeping track of the broken stuff. Steve Bauer at MIT has been studying this in a really major way. He's probed the top 1 million or so Alexa websites to see what's going on there, and he's looking at some other stuff. He did some preliminary reports on this at the Kaida workshop in February. On my blog is a pointer to his slides. So you can see a bit of the work in progress he's doing to try to understand how much is broken. The actual state of deployment on the server side is going decently well. It's gone from about 1% capable of supporting ECN to, I think the number was 12 to 14% in the last 2 years. And if you look at the timing of when the operating systems released with server ECN support enabled. In other words, a server is willing to talk ECN if the client says it wants to. If you look at the timing of that, that's actually not too bad a result. It does seem to be getting deployed. And of course, particularly in particular point areas like to handsets and the like, where the traffic patterns may be quite different than from the home, where a lot of the broken kit may be. We may be able to use it, we may not. I don't know. I mean, that's research that we need to do to know if we can start really using it.
If you'll forgive me for intervening, I want to make sure that we have a formal thank you for our speaker so that I can sneak out before more dirt is cast at the TCP than already has been cast.
Oh, by the way, Anything can fill these buffers. UDP can just as easily fill them.
No, I
Okay?
understand. I understand. I'm just making a bad pun. Anyway, Jim, I really appreciate your coming out and raising this as an issue. I hope there's something that we can do to contribute to the solution. So let me formally close the session. You can stay here for as long as you can stand it, and people are wanting to ask questions. But let me officially thank you very much for taking the time.